Okay, alright, so let's play the following game. I'm going to start with some random triangle. It doesn't matter what this blue triangle is. It can be anything, right? I have several triangles that I can pick from. I'm going to pick this particular one here. And I'm going to elect a point in the plane, for example, x6, which is its Symmedian point. And I'm going to make this triangle turn about rigidly, turn about its Symmedian point. So let's animate that. So here it is. So I have a family of rigid rotating, a family of triangles rigidly rotating about its stationary Symmedian point. Very well. I could actually show the locus of each one of its vertices. Let's go ahead and do that. There it is. So obviously, if this is a family of triangles rigidly rotating about a fixed point, uh, every one of its vertices is going to follow a circle centered on that point. And this point happens to be x6. I picked x6, the Symmedian point, for a very special reason. Let me introduce a new player in this game, which is an inversion circle. So I have a circle here, this dashed green circle. Let's call its center O. I can play with its radius, of course, and I can play also with the horizontal location without loss of generality. You'll see why, of its center. So I can place this inversion circle anywhere. Okay. Now here's what I'm interested in. I actually want to now draw a triangle whose vertices are the inversive images of these three blue vertices with respect to this circle. So I'm going to be using geometric inversion. Okay, so let's go ahead and draw this inversive triangle. Okay, so here's a triangle with three red vertices, which are the inversive images of these three blue vertices with respect to this circle. I'm also drawing what I'm calling here x6 to the minus 1, the Symmedian point of this, what I'm calling inversive red triangle. Okay, now a miracle happens here. First of all, you can already observe this. X6 of the original triangle, the center of inversion, and the Symmedian of this inversive image are collinear. I can move my center of inversion anywhere, and the collinearity persists. You can see here that at some point, and this is going to be important for other phenomena we're going to cover later, there's a particular position for O where the red triangle undergoes what we call an eversion, okay? Meaning that the sort of larger side is going to cross over to the other side, okay? So that's called an eversion, but this is beyond the main topic here. So let's just now look at what happens to this inversive image and the fact that the inversive Symmedian, x6 to the minus 1, which is the Symmedian point of this red triangle, remains collinear with O and x6 of the original triangle. Of course, I can also change the radius of my inversion circle, and this is actually a more trivial phenomenon in that all you're doing is actually changing the scale of the red triangle. Okay, so there's no real geometric action going on here other than this isotropic scaling of the red triangle, and I maintain the collinearity. Okay, so the interesting geometry that does change is when you actually slide the center of inversion around, and you could study what's going on with this family of triangles as you slide the center of inversion around. But this is not the main central topic here. The central topic here is what is going to happen to this family, specifically to the red family, once I go back to my original game, which was to make the blue triangle pivot rigidly about its Symmedian point. Let's go ahead and fire that up. So when you do that, a very cool miracle happens. The Symmedian of the inversive image not only is collinear with x6 and O, but it's also stationary. And that does not depend on the geometry of my inversive triangle, which I can change as I move O around. For example, let's leave O here. You can see that x6 remains stationary. So this is a pretty cool phenomenon. I'm going to cover more phenomena in the next few videos about things that relate to this. Let me show you one more thing here, which is what is the locus of the vertices of my red triangle as the blue family rotates. So let's go ahead and show that. I'm calling this the inversive loci, and let's scale this out. You can see here that the red triangle is going to, each one of its vertices is going to be moving along an independent circle. And this is to be expected because the inversive image of a circle is another circle. And what do I mean by that? Let's actually move OX a bit to make these three circles become more visible, like so. I'm going to go ahead and scale this up again, and I'm going to move this to the right a bit. So what do I mean by this? If you recall, the three vertices of the blue triangle are each moving along its own independent circle, correct? So there you can see that, these light blue circles. So what this implies is that each one of the vertices of its inversive image is going to move along the inversive image of each one of these circles with respect to my center of inversion or to my inversion circle, which is this green circle. Okay, so I can expect that each one of the vertices of my red family is going to move along its own circle, which is an inversive image of the circles, these three light blue circles. And let's look at them again. This is it. And there are these sort of orange circles. So the red triangle family is a family of triangles. Let's slide this to the left a little bit. Where each one of its vertices is moving along an independent circle. And these circles are inversive images of the original light blue circles. Now, remarkably, despite the complexity and the inversions, you can see that this triangle, the red triangle, it is undergoing an inversion. What do I mean by an inversion? Let me go ahead and do this very slowly here. As this triangle advances right here, as I get close to this position, I'm going to do this manually. You can see here that the long side of the red triangle is going to change sides. Okay, so the long side, if I go back a little bit, it was like that. Let's go back even more. I was in this position, and as I advance, I start becoming thin, or the red triangle starts becoming thinner and thinner, and at some point it undergoes an inversion, which means that one of its sides goes through the opposite vertex and the triangle changes, so that that long side changes sides. And what's really crucial to understand about this phenomenon is that the circumcircle of the red triangle, which I can show here, the circumcircle of the red triangle, and I thought I had changed colors, I have not. That's fine. So the circumcircle of the red triangle, which is represented here by this dash purple arc of a circle, if I go back a little bit, you can see that the circumcircle was in this position, and in the inversion, it switches over to the other position. So the circumcenter is over here of the red triangle, and as I go back, the circumcircle goes through infinity and comes back through the other side. Okay, so these inversions turn out to be rather important for the analysis of other loci that we're going to see in other videos. So here you can see simultaneously the well-behaved circumcircle of the blue family, which is this solid purple circle, and the side-switching family of circumcircles of the red family, the dash purple circles. Though this does not bear any influence on what's happening to the position of the Symmedian point of my inversive image, which remains stationary for whichever location I choose for my center of inversion. Okay, so we're going to see more phenomena in upcoming videos connected with this one. See you on the next one.